this week, which is general purpose I/O ports. This requires you to actually know a little bit about electrical engineering. Nothing difficult, but you should know because uh, this is really a fundamental concept you should know. And a lot of times, if you don't know the concept, your system might not work. Okay, so it's very important you know how it works. At least this is the minimal electrical level you should know. Nothing difficult. So what's a general purpose I/O port? Well, so there are actually the concept of a port and concept of a pin. Okay, and they are different. So depending whether you're talking about software or hardware, you're right at the borderline between hardware and software. Okay, now so from the interface point of view, you can treat general purpose I/O ports as basically what's called software controllable pins. And by pin, I mean you can actually see and probe it, right? Whereas if it's a register, it's inside the chip. You can't do anything to it. You can't look at it. Whereas a pin is exposed. That's hardware. That's real hardware with a voltage on it. Okay. So yeah, I guess one simple definition is it's a software controllable set of pins. And you can read and write these just like registers, or more specifically, special function registers, SFRs. Okay. But the issues are, well, are you accessing one bit at a time or one byte at a time? Right. Also, I/O means input slash output. What does slash mean? And in fact, I really don't like to use the symbol slash because I think it's totally ambiguous. It could mean and, it could mean or, it could mean either or, it could mean lots of things. It's a sloppy way to write things. So in my writing, I usually avoid using a slash. But people nowadays like to use a slash as a sloppy way to say it's any one of those. You just decide for yourself. Well, um, no, but this I use I/O because that's what everybody else calls it. It can be for input, can be for output. But how do you specify whether you want input or output? Well, it turns out it's both. It's inputting and outputting at the same time. Okay, and I'll show you why. But that's one way to do it. Of course, there are other ways to do it. Okay, and you uh, choose the direction explicitly. But in Intel's way, you are always outputting, even when you're inputting. There are ways to specify drive strength. I won't talk about drive strength yet, but later when we see the CC2540, then we'll see how it controls drive strength. For now, I just want to go through the basic concepts. That means how hard are you outputting the value. And by hard, that could mean amount of current, and things like that. And then we'll also take a little look at the overloading with other types of I/O functions. What this means is, in any chip, especially microcontrollers, the number of pins is usually a big issue because the chip inside is tiny, but as soon as you have to connect a pin to the outside of the package, that takes up room. You might think, oh, that's so tiny, but to a chip, it's huge, and it costs a lot of power to drive a pin. So the more pins you have, the bigger the chip is, the larger the package. Takes up more room, takes up more power. Usually that's a bad idea. So many chip makers try to keep your chips small and minimize the number of pins they give you. But then that sometimes is not as convenient. And that conflicts with providing as many features as possible to you. So what happens very often is they reuse the same pins for different functions, but you have to choose one out of n functions at a time. And one of those happens to be general purpose I/O. But if you're not using those pins, then you can configure those pins to be some other functions. Okay, so they reuse a lot of the same pins, just because having too many pins is costly. Okay, so this is actually the original 8051 package. It comes in, or it came in a dual inline or DIP package. So that looks like a bug, right? With lots of legs on the side. And if you use breadboards, right? These are designed for breadboards. Breadboards are these prototyping boards, usually white, and a few rows of these things, and then you push one of these, and then they connect, right, on two sides. And these will have a little notch on the top to tell you which way is up. So the little dip on the top, that indicates that's the way it's up. And then the power and ground are always on opposite corner. Right? The power is always upper right, ground always lower left. At least within the dip package. Now, of course, no, we're working mostly with like these SMT and other packages, and they don't look like this anymore. But it's still useful to know what this used to look like. Now, the original 8051 had 40 pins, 20 on each side. Okay, and you take a look and wow, okay, it has 4 ports: P0, P1, P2, P3. And they take up 32 out of 40 pins. Wow, that's a lot, right? Like the overwhelming majority of the pins are used for general purpose I/O. I mean, you need a power and ground, so you minus 2, and that's only 6 pins left for all these other functions. And 2 of them are for the crystal. Okay, 4 other pins, and those are really just for supporting external memory. So everything else goes to GPIO. This shows you how important GPIO was, at least at that time. Things have changed since then because people thought, wow, that's too wasteful, too general. So they invented other types of interfaces that don't require as many pins. But this was really optimized. At least the original 8051 is really optimized for general purpose I/O. Okay, because with general purpose I/O pins, you can control exactly which pin you want to turn on, turn off, in what sequence, and so forth. Okay, so and really, I mean, just take a look, right? 32 out of 40 pins, and so that's a lot. But that doesn't mean it can't do anything else. Because if you take a look, there are other names in parentheses. So I don't know if I can zoom in. I'll try. Yeah, okay. You see there are like the P0, and then there's a parenthesis, AD0. So it's something parentheses, right? So instead of its primary function, like the P0 P0.1, it also has the secondary feature in parentheses. Okay? So that's something to pay attention to and think about. And then if you look at P3, there's P3.0 is the primary function, and then there's RxD. P3.1 has the secondary function TXD. Those are for the serial ports. Okay, and then the int 0, int 1, the T0, T1 are WRRD. So yeah, those are for other secondary I/O functions that are not general purpose I/O. And the rationale is that you might not need all of these general purpose I/O pins. When you don't, yeah, then you can use those unused pins for their secondary functions. And these are just the original 8051 definition. In newer chips like the CC2540, we'll be using, there are many, many other secondary functions you can possibly use. Okay, so you may have to configure your microcontroller to say, oh, I don't want it to be a general purpose I/O port. I want it to be something else. How do you do that? Again, through special function registers. Okay, so you need to know what SFR to use to let you choose one or the other functions. Okay. Now, so 8051 has these four I/O ports: P0, P1, P2, P3. At least the space is defined for them. Later 8051s don't necessarily implement all four of them. They might implement maybe P1, P0, P1, and maybe P2, sometimes even partially. Like the CC2540 actually has the address for P3 but does not have a real port for P3. That happens too. Okay. And now, so but anyway, each one of them is mapped to one of the special function registers, and so you can move values to or from these special function registers. And as part of the move, you can affect the values on the pins, and these are external to the package. Okay, and also all these four are bit addressable.